All right, I'm not going to lie, I didn't quite finish making the slides like I had hoped to, so the last bit might be more like a whiteboard using the iPad, but hopefully that's okay. All right, so today's topic is dimensionality reduction, which is a very practical topic if you're doing anything related to quote unquote big data. Oh, as usual, we got to do a quick rewind. Uh, so just to recap, our first lecture was about linearity of expectation. Our second lecture was about hash functions and Markov's inequality. The third lecture was about linear probing and hash tables. That was followed by, that's no longer last Thursday, randomized algorithms for minimum cut. Then we did random graphs, but in particular, we made friends with the multiplicative Chernoff bound. We then did randomized rounding for a lecture. And then finally, last time, we did distinct elements, which is also introduced variance, Chebyshev's inequality, and the median trick. All right, so that brings us now to today's lecture about dimensionality reduction. But really, it's going to be a story about Gaussian random variables. And maybe the takeaway is going to be that if you understand these things very well, then this is in fact very easy. So, all right, I'm sure half of you will have a thesis where big data appears somewhere in the title. So, what does big data mean? Well, I guess there's maybe at least two interpretations of the word big. One that we've already done is when you have many like pieces of data, right? So something like the streaming model, where the number of pieces of data coming in far exceeds the size of your computer, so we only kind of process one item at a time. And then problems like figuring out the heavy hitters or distinct elements suddenly becomes non-trivial because you can't store every little piece, right? So that's maybe one sense of the word big data. Maybe the other sense of the word is when the individual pieces of data are very big, and often we're dealing with high dimensional vectors, so big arrays with tons of numbers. Okay, so that's another sense of the word big data, and then of course you can have both. So let me give some example, or maybe I can open up. Does anyone want to give me an example of a situation where you can get very high dimensional vectors naturally? That maybe you've come across in your own work. All right, let's look at some examples. All right, so one is called bag of words representation of text. So someone tell me, give me a sentence, any sentence. Literally any sentence is fine. Just someone say something. Okay. This happens every year. You think you're creative, but every year everyone does the same thing where they do some clever repeat back whatever I just said. Okay. Whatever, but you have a snippet of text, right? So how do they represent this? Well, they make a vector with one entry for every word in the English language. And they'll just count up how many times each word appears. So maybe this slot in the array corresponds to literally. There will be a 1 there. Over here might be any. There will be a 1 here. Sentence. There will be a 1 here. Maybe is. It's too small. There will be a 1 here. And then I'm fine or something. Okay. And everything else is all 0 because there's no other words in this wonderfully creative sentence. Okay. So this is sometimes called a bag of words representation. It's just counting up the number of each word, right? And of course, implicitly the dimension is huge because you're making basically a slot for every possible word in the English language, not to mention typos like you find in the lecture notes. Okay. All right. So that's a natural way to generate extremely high dimensional vectors. All right. If you want to take this and put this on steroids, sometimes they're interested in something called bag of phrases. So if again we did the sentence literally any sentence is fine. Okay. So this time, rather than encoding every word, that's not how you spell fine at all. You know, I actually won the spelling bee in like first grade. I have like a little like crown with like anyway. Uh, but I think so I've regressed. Anyway, so in bag of phrases, it's like bag of words, but these are models that are also kind of interested in words that are co-occurring next to each other, right? Phrases have meaning. So rather than sort of doing a hot encoding of all the words, they'll encode all the phrases, right? So maybe 3 words at a time. So one would be literally any sentence, and there might be some entry here for literally any sentence. That appears once. And another phrase would be any sentence is. So that'll also correspond to a slot. Something like that. Another phrase, sentence is fine. Okay. So last time we said that for a bag of words, maybe the dimension is something like the number of words in the English language. If I was doing bag of phrases, where a phrase is defined as 3 words, what would that dimension be? It'll be less than infinite, hopefully. But yeah, it'll be big, but maybe sharper answers. Yeah, maybe number of English cubed. Number of words in the English language cubed or something like that. Okay, so the point is, you can be a little bit creative and easily generate massive vectors. All right. What's another example where you get a very, very high dimensional vector? Maybe if you have very large networks and you're writing them down, right? So maybe you can look at like the adjacency matrix. So the World Wide Web, you can model as a graph. Each website is a node. You have edges between them when there's links, right? What would be like the dimensions of the adjacency matrix for the World Wide Web? All right, something like number of websites. Times the number of websites. So these are very big. You can think of, first of all, a big square as one extra long vector, but even also the individual rows, which represents the neighborhoods of various vertices, those are also long vectors. Okay. Okay, you can also think of social networks as a graph. What are the dimensions of a social network? All right. Okay. So, we have lots of people on the social network, probably more than on planet Earth, and whatever, you get the idea, right? Okay. Okay, so the point is big data rises naturally, right? Now, with these vectors, what do the algorithms really need? So at some level, you have various like clustering algorithms or numerical algorithms or something like that. And of course, having the full representation of the vector would suffice. But at the end of the day, usually these algorithms are, maybe taking the dot product of various vectors, or maybe they're measuring the distance between vectors, right? They want to know how similar one sentence is to another. Or they might, the length of a vector. stuff like that. Okay, but they're doing some kind of linear algebra kind of thing. The point being, though, if we can just provide this information in some clever way, we don't necessarily have to store and write down all the vectors in their full detail, right? So keep that in mind. And moreover, in many cases, just being able to approximate these things, getting like 5% error on all the distances or something, is fine. You'll get 5% error maybe overall, but it'll play nice with the overall algorithm. Okay, so we don't have to necessarily be exact either. Okay, so, all right, so this class is about how do we deal with these really, really high dimensional vectors. In particular, they're too big to really store in memory. Of course, you can do a sparse encoding of a vector, right? So instead of actually making an array, you just use a hash map or something. But things get trickier as soon as you start like, adding vectors together, subtracting one vector from another, then it starts getting dense very quickly. Okay. So at some level, the real question is, can we maybe come up with smaller vectors that preserve the essential information, but isn't infinitely big. Okay. All right. So, okay. So then I guess the moral then of dimensionality reduction. How many dimensions do you really need to capture some of these geometric properties of your data? If you're looking at n points, so n vectors, and you want to say preserve all pairwise distances, we will show that you actually only need about log n dimensions. We'll be able to compress it. Okay? No matter how big the original input dimension was, we're going to be able to get this down to log n dimensions, which is incredibly, incredibly modest compared to those examples from before. Right? So this is a huge win. So let me elaborate then. So what we're going to do is we're going to construct some function f. It'll be a very simple function, turns out, that takes as input some large vector from an extremely high dimensional space, outputs a randomized vector in log n dimensions, with the guarantee that we can preserve all distances between any pair of points up to a 1 plus or minus epsilon approximate factor. Okay, so there's some, you need log n over epsilon squared dimensions, so there's some trade-off. You want more accurate, you pay a little bit more in the output dimension. Okay, that's really what we're going to prove today. Okay, spectacular theorem. Let me give you the more detailed version now. So I just copied this from the notes so that I don't make a mistake. Okay, so our function is going to be a very simple one. F of x is up to scaling equal to ax, where a is going to be a matrix. Okay, so the output dimension is small, k log n over epsilon squared. The input dimension is very big, so you should think of a matrix that looks like this, like very, very wide. The output dimension is very small. And for every entry, we are going to sample what's called a random Gaussian element. Okay, so every entry of this matrix will be randomly sampled from the Gaussian distribution, the normalized Gaussian distribution. Okay, so and that's the whole function. So when you're applying ax, x is some vector like this, and it just gets multiplied against a bunch of Gaussians and output. Okay, there's nothing particularly sophisticated about this construction. In fact, A has nothing to do with the input points, right? So this is called an oblivious embedding because it doesn't look at the structure of the input or anything like that. You give me any points, and I'll do this random sampling and use that to create a low dimensional embedding, and it's going to preserve all the distances with high probability. All right, so when I first saw this, I was amazed. Didn't think that was possible or anything even remotely. I would have been impressed if we got square root n dimensions or something like that. Log n is amazing. Okay, and what's even funnier is that if we were comfortable with all the properties of a Gaussian random variable, which we will become soon, uh, in fact, this is completely obvious. That's the main takeaway. Okay. All right. So any questions about this algorithm or this kind of input and output and this interface that we're going to try to prove? Because it's weird, I would think. We haven't looked at anything that looks like this before. Yeah. Yeah, okay. Okay. So this is a little bit more of a mathematical fact that if you had a full set of Gaussians and you multiplied it with x, uh, it would be great. So, okay, so a couple things to keep in mind. So you only have to, first of all, apply the columns where x has a non-zero entry, okay? And the number of rows is roughly log n. So each non-zero of x gets multiplied against log n numbers, so it's like log n times the size of x. Now, one thing that might come up is, okay, if the input dimension is so big, why would I want to make so many Gaussian random variables? I don't want to make an infinite number of Gaussian random variables. So there's more sophisticated constructions that'll replace the Gaussian sampling instead with like plus or minus ones, okay? And moreover, the plus or minus ones are going to be generated randomly by hash functions. So you don't actually have to write down all the plus or minus ones. You just have a hash function that implicitly represents uh, the matrix. So that if I just want to say, okay, I just need to get these columns of numbers, I can just look up the appropriate hash. Yeah. But structurally, it's going to follow the same way. The only reason why these the hash versions work is because actually plus or minus ones behave similarly to Gaussians for technical reasons. Okay. This is a very practical thing that's used quite a lot. All right. Yeah. Okay. Everything today, sorry, is in the L2 norm. Sorry. This kind of thing. Euclidean norm. And your second question? Oh, yeah. So is there a generalization to higher dimensional, or if X is a matrix? I mean, I think basically the answer is yes. Um, uh, so okay, maybe I'll say something else. So maybe this is, first of all, you should think of this as our first example, or maybe our only example in this class, of this kind of oblivious embedding, randomized projection, getting smaller dimension. But the general idea of taking big objects, turning into small objects, but roughly preserving the mathematical geometry is more basic. So if you're trying to take big matrices and kind of shrink them to smaller matrices, your criteria might change a little bit as based on what you need from matrices, but absolutely there's interest in making smaller matrices too. Other approaches for matrices also include like low rank approximations and stuff like that, which is writing matrices as a few rank one terms. But that's also roughly reducing the input size or reducing the size in a lot of ways. That's more structural, but Um, yeah, and some of the well, at least one of the homework problems will maybe poke at like an extension or a different kind of dimension that sort of is related to some of this stuff. So yeah, there's a lot of stuff out there about using randomization to kind of obliviously shrink the size of things. Um, yeah. Oh no, no, this should be NP. Okay, yeah, that would be too strong. That would be impossible because there's some pigeonhole issue. Yeah. Oh, there's a hole for any P norm. Uh, well, first of all, there's always some relation between two norms and P norm. I mean, uh, so you'll get like different factors. There might be like you'll get different relations. To get 1 minus epsilon, you might need to use more dimensions or less dimensions or something like that. Um, yeah, some level, yes, but it gets messier. Um, yeah, and mm, so later we might do, for example, something called L1 embedding. So that one's about the L1 norm. And so L1 norm, if you guys remember, is just adding things up. X1, absolute value of X1 plus absolute value of X2, absolute value. So that has a much more combinatorial flavor, more kind of used to what we're used to, like graph algorithm. So those kinds of embeddings, rather than doing this kind of Gaussian stuff, always plays much nicer with the L2 norm and Euclidean space and stuff. But for the L1 norm, we'll actually do like crazy things uh, based on like trees and graphs and stuff like that. So people are interested in other P's and Q's, but sometimes they have a different personality altogether. Um, L2 is the calculus is always nice in L2, right? And Gaussians are basically an exercise in calculus. All right, these are good questions. All right, no more questions. All right, let's see what comes up. All right, so again, what I hope to convey is that if we come to learn and appreciate Gaussian random variables, then the surprising projection theorem, in fact, is not so surprising. That's what I really want to convince you. Let's see if we succeed. All right, so I guess you guys have probably been exposed to some extent to Gaussian random variables before, the normal distribution. So often we write, this says that X is drawn from the normal distribution. And it's a distribution that has two parameters, mu and sigma squared. Mu represents the mean, sigma squared represents the variance. So X will have mean mu and variance sigma squared. Does anyone know the definition of a Gaussian random variable? Yeah. Okay. A density function is exponential. You know that formula that he's referring to, like 1 over square root 2, stuff like that? Okay. So that's the wrong answer. For us, we are defining Gaussian random variables as the nicest, most pleasant, and convenient random variable ever. Okay. So let's see. Let's see why. So what we're going to do is we're going to go through some of these very nice properties, these as facts, just to build some intuition. Get enough facts down so that we can do that theorem and see why it follows from the properties. And then we'll go all the way back to the density function, recover the facts, and put everything together. But I think that one of the nice takeaways about Gaussian random variables is they're just so nice to manipulate and play with. In the same way the ideal hash functions are the easiest to work with and stuff like that. And that's what I would like to emphasize. So here then is for example one fact. So let's say that I have some Gaussian random variable x, mean mu and variance sigma squared, and I have some constant alpha. Okay. Now x plus alpha represents some random variable, right? But in particular, it's actually distributed very nicely. What can we say about x plus alpha? Yeah, so it's also distributed as a Gaussian. The mean is shifted, and the variance stays the same. Okay, nice little algebraic property. I can also multiply. I can do alpha times x. What's that distributed like? Yeah, so actually, if you guys remember, but the variance of alpha x is equal to, so it actually goes up by alpha squared because the definition expands to a squared kind of thing. I mean, the definition of variance, so there's a square coming out. Okay, so the nice thing is that, you mess around with x a little bit and it's still a Gaussian. Right? That's very convenient. With the mean and the variance sort of changing exactly as required by the definition of expectation and variance. Okay. All right, so that's one nice fact. Here's another one. Suppose you had two Gaussian random variables and you add them up. What do you get? Yeah. Yeah, so I guess the main thing is that you get another Gaussian, and if you do, the mean has to add up, and actually and the variances will also add up, right? But this is so nice. It's always so nice with any mathematical object when you can combine them and stay within the same class of objects. So here, we can combine Gaussians and get Gaussians, right? That's not true of, let's say, 0, 1 random variables. If you add up two 0, 1 random variables, you get a 0, 1 or 2 random variable. It's no longer what it used to be, right? So whatever tricks you had for 0, 1 don't work anymore. But here we can keep analyzing roughly the same thing. Okay. This one is a little bit more technical. I don't know how anyone's going to guess it, like we can try. I'll only try to give some high-level motivation for the moment. When we proved the Chernoff bound, we turned out to be very interested in something that kind of looked like this, analyzing the expectation of some random variable exponentiated. And insofar as this was well behaved for 0, 1 random variables in the proof of the Chernoff bound, everything kind of went through nicely. Okay. So likewise, we have some interest in analyzing what's called the moment generating function of x squared, where x is a random Gaussian. Okay. And as a matter of fact, actually, no, we're not going to analyze this just yet. So as a matter of fact, this has a very nice closed form of square root 1 over square root 1 minus 2t. It feels a little bit miscellaneous or technical at the moment. So maybe all I will point out is that A is an equality, so we're not doing any sloppy approximations in the middle to get this. And it's relatively clean compared to, say, even a density function. Okay. All right, so there's something nice going on technically. Fine. Okay, so that's the third fact. That's the most obscure one, but we'll prove it later. I have it written on the right. Okay, so now we were interested in analyzing matrices where everything is Gaussian, but as a baby step, let's analyze vectors where everything is a Gaussian. So this notation where we have this k in the top right, Gaussian to the k, what it's saying is that x is a randomized vector where every coordinate is independently sampled from that Gaussian distribution. Okay, so you have k Gaussians. Right? Okay. right. Okay, so let's say that, let's look at the special case where x is sampled was mean 0, but otherwise is that variance. Okay. What is the expected value of the length of the vector? Or how would I go about it? Okay, so I'm looking at a vector where every coordinate is a Gaussian. Now I'm asking, what's the expected Euclidean length squared? Again, everything is in the L2 norm. Yeah. Okay. So I'll write the sum. We can go over all the coordinates. I realize that maybe some of this notation may be slightly unusual for some of us, but we'll get used to it. So just ask questions if all the vector notation and the stuff is going too fast. Okay. All right. So the norm squared, ultimately is hiding a sum of squares in there. And so we just apply linearity of expectation. Now, what's the expected value of one of these xi squares? That's just a variance. Okay. So that's right. So you get k times the variance. All right. So one thing we're going to be very interested in is not just the expected length squared, but how close or with what probability is the length going to be close to its expectation? So it's okay, the expectation has a very nice clean form, but the real question is it concentrated at the expectation? Okay. All right, so this is maybe the technical version, and then a cleaner interface will come up afterwards. So we're looking at a vector x, a k-dimensional randomized vector. Each coordinate is a Gaussian. So the first one is saying, so alpha is some value less than 1, like alpha is 1/2 or something. What is the probability that x is much smaller than its expected value? Okay. And I guess the technical thing is alpha e to the 1 minus alpha to the k over 2. So maybe we can just plug in, for example, if alpha was 1/2, then you would get like 1/2 e to the 1/2 to the k over 2. Okay. All right. So for anyone who doesn't, 1/2 times e to the 1/2 is something less than 1. The most important thing, some constant less than 1. Okay. But then you have a k over 2 in the top right corner. So in particular, the odds of deviating is going down geometrically or exponentially fast in k, right? So the higher k is, the more concentrated the length is. Okay? So it turns out that a high dimensional or even moderately high dimensional Gaussian vector, meaning every coordinate is a Gaussian, the length is extremely well concentrated at the expectation. I guess we should do the second part. So the second part, of course, is what are the odds is much bigger. And again, you'll get something less than 1 to the k. Okay, so this is a very important fact about Gaussians, is that the length of a random Gaussian vector is extremely well concentrated, especially for higher dimensions. That's really what we're going to take advantage of when we do our random projection. Okay, so we can prove this. We'll need to use that obscure fact, but that's okay. Okay, so let's first look at that case where alpha is less than or equal to 1. We'll do that together, and then if you guys find it really boring, we can skip the other side. Okay, but we should do at least one together. Okay. All right, so we'll start with, okay, what are the odds that x squared is less than equal? Let's make things a little bit easier. So up to scaling, these are all the same. So I'm just going to worry about the case where the variance is 1. Okay. In that case, the expected value of the length is k as opposed to k sigma squared. Okay. And everything's the same up to scaling, and it's less notation for me, which is less notation for you. Okay, so that means I'm worried about the probability that the length squared is less than alpha k. Okay. All right, so you guys might be able to guess some ideas of how to get started on this. Yeah. Okay, we're going to exponentiate. So now, okay, so let me do first something. So the most natural thing is, I guess we're going to let t be a parameter to be determined. Last time I was told t is a bad choice. Should I not use t? Would you guys like me to use something other than t? I was told t looks a lot like plus. I can use tau. That's awfully similar. All right, t it is. No opinions. Okay, so here I've exponentiated both sides, right? But now what? Yeah. We can choose the left, sorry? Oh no, well, okay, so what step, yeah, what step, that's true. Okay, so we can do that. That's fine, but okay, but it's still the same. Nothing's really changed. That's just expanding some notation. But you can't, so you're missing a step though. That will come later. That will come later. But yeah, do you guys remember what comes roughly next in the Chernoff proof? I know we did it very fast. Or in any of these proofs, you know, right now we have this p, right? We always got rid of the p somehow and turned it into a different kind of calculation. Markovs, okay, we can use Markovs, except we can't. Why can't I use Markovs here? Oh, it's the wrong sign. I want to do greater than equal to. All right, how do I make that into a greater than equal to? Inverse. All right, so we're going to add a negative sign. Okay. And then you can flip the inequality. Now we can apply Markov's inequality. E to the t alpha k, because it's negative t alpha k, and it cancels out. Okay. All right, so now you can do the thing where you break things up. All right, so let's just worry about this term for a while. Okay. E to the negative t xi squared. Expected value of. Okay, so that's just because we used to have the sum of xi's in the top right corner, and then we did the usual. You can break up the exponent, the sum, and yeah. Okay. All right. What comes next? Yeah. The weird fact. The weird fact. So it turns out each of these, we need to assume that t is less than 1/2 for this to work. So these are each square root 1 minus 2t to the k. Okay. So that's something, yeah. Oh, good point. Yes, it is. That's good. And that's useful. Okay. In fact, maybe this notation is a little bit easier if I put k over 2. Okay. So at a high level, what do we have now? 1 over 1 plus 2t, k over 2 times e to the t alpha k. All right. Okay, so fine. Now all that's left is to choose the best t. Okay. So one way to do this is sort of, okay, we can do some. So this is equal to e to the, how would I write this? K times alpha t minus 1/2 ln 1 plus 2t. Okay. And I only put it in this form because then I only have to look at this part to try to find the best choice of t. I want to make that as small as possible. Okay. All right. So if you do the calculus, uh, this is minimized. I don't know if you guys want me to do this slowly, but it turns out, you just take the derivative and make it equal to 0, and you rearrange some stuff. And you'll get that the best choice of t is 1 minus alpha over 2 alpha. Okay. And you plug that back in, and apparently, well, you guys can tell me if you disagree, but I got alpha e to the 1 minus alpha k over 2. Okay, fine. All right, so whatever, you plug it in, and now it comes that bound. Yeah. So at the end of the day, we got this is less than equal to this. Uh, so you want one of these to be less than? I can give you all of them. Oh, this one? No, this is equal. This one's actually equal because you exponentiate. It nothing to do with convexity. Just because exponentiating preserves order. So if a is less than b, then e to the a is less than e to the b. Just because exponentiating preserves the order of elements. No, we're not using convexity. We're not using convexity. It's just so I'm just using this kind of thing. Uh, just a is less than b if and only if e to the a is less than e to the b. So I'm not using any convexity. Um, okay, maybe we can figure it out after class if there's more confusion. Okay, let's figure it out after class. All right, so what's the point? Okay, so roughly, so that what we proved is this one. You might imagine the second one is proved similar. Yes, question. Yeah, okay, so for t to be less than 1/2, let's double check. That means we need 1 minus alpha is less than alpha. That means we need 2 alpha greater than 1. Good question. Oh, actually, here it's not an issue. Okay, it's because we have this negative sign that you pointed out. So we actually need, okay, so RT is actually negative t in the fact. So actually what we needed then was negative 1 minus alpha over 2 alpha less than 1/2, which is, I think, simply true because this is a positive number, it's a negative. Yeah, so that's the other side, actually, yeah, if we had, well, if you guys want to, we can. But I do, if I recall correctly, when we do this side, actually, it's a little bit more narrow. It barely works out for the other one because you don't have the negative sign. You have to actually double check. But here, actually, the signs are working in our favor. So it's, yeah, that's a good point. All of these things are barely work out, and they worked out once. Where are we? Okay, it's a little bit technical. I think maybe the high level, the moral takeaway though, or if one moral besides just doing calculations, is that whenever we're getting these very strong tail bounds and concentration bounds, we seem to be doing roughly the same trick as we ramp it up by exponentiating and then we break it up into exponential, and somehow that seems to make a big difference. And the fact that exponentiating a Gaussian squared is really well behaved, we have that nice clean form solution, is really something that enables things to go through. Okay, so, and that's a general principle. So insofar as whatever, if you're looking at concentration of a bunch of little stuff, and if exponentiating the little thing by itself is kind of easy to work with, then you have some hope of getting a tail inequality. So that's really the only reason why we needed a 0, 1 random variable for the Chernoff bound, is because if I know the variable is small, then I know that e to the x is roughly 1 plus x squared, and so things are nice in that regime as well. That's maybe a moral thing to keep track of. Okay. All right. So I left space for a second one, but I'm guessing not too exciting. So unless you guys want me to, just anyone want to see this one? I got one hand like this. Yeah. Okay. So if we had plugged in alpha is equal to 1/2, um, uh, okay. So if alpha, okay. So okay. So one thing is that alpha is actually only sitting in the uninteresting part of the calculations. Uh, This is the part that is more interesting and related to the Gaussian random variables. Uh, oh, yeah, let's just plug in 1/2. Okay, so let's look at 1/2 e to the 1 minus. Oh no, alpha needs to be bigger than 1. So this one I'm looking at. Okay, so let's just go through it. Okay, what are the odds that x is bigger? This is the case where alpha is greater than equal to 1. So we can plug in maybe alpha equal to 2, for example. So if I plugged in alpha equal to 2, my bound would be, well, it's the odds that x is 2 times its expected length is at most 2 times e to the 1 minus 2 to the k over 2. Okay, so that's 2 over e to the k minus 2. E is rumored to be 2 point something, right? So 2 divided by 2 point something should be less than 1. And then again, now we got the k over 2, so it's going down very fast. Yeah. Okay. All right. And then the proof will be similar. And then it is true that this part will be a little bit more delicate, checking to 1/2 if I remember correctly, but the details are all there. The main thing is we use this fact. Okay, I did leave some white space though. All right, so here maybe is a more convenient form for us because we're often looking at kind of relative approximations close to 1. So here I'm basically replacing the alphas with 1 minus epsilons and 1 plus epsilons for convenience, because the right-hand side is much cleaner now than before with the alpha e 1 minus alpha. Okay, so, all right, what are the odds of being 5% smaller than the expected value is e to the negative 0.05 squared times k divided by 8. Those aren't the tightest possible constants. There's better constants in the notes. And then what are the odds of being 5% bigger? Okay. So I think this is nothing more than plugging in for alpha. Okay. So if we remember that before we had, let's say for number 1, we had alpha e to the 1 minus alpha to the k over 2. And now alpha is equal to 1 minus epsilon. Okay. So you get something like 1 minus epsilon e to the minus epsilon. Okay. To the k over 2. Okay. And let's see, there's different ways to do it. So one is e to the x is less than or equal to 1 plus x plus 1 half x squared for any negative x. Okay. Last time we did less than or equal to 1 plus x squared for x less than or equal to 1. But anyway, the 1 half doesn't matter too much. Okay. No, that's not what I want. Okay, let me do it a little bit differently. Okay, so a different one. All right, there's a different one, which is 1 plus x. So it is true that 1 plus x is less than or equal to e to the x. Uh, in fact, it's even smaller. So assuming that x is, say, at most 1, it's at most c times x squared, where c is some small number. Like I worked out the best possible one, roughly 0.307. Okay. But if you plug this kind of thing in, you get e to the negative epsilon. Oh, I'm sorry. Is this what you said? Is this should be e to the epsilon? Good. Okay, this is what was messing me up. All right. Um, this kind of thing. Okay. For some constant c, which is, I guess, bigger than 1/4. Okay. All right. So, uh, good, good. All right. So roughly plugging in and then messing around with the usual approximations of e to the x. This one we use a slightly tighter one. Gets us the bound we seek. Okay. All right. Not too excited. It's mostly technical. All right. So, all right. But now we have these facts all along the right. I don't know if it's big enough to see. Okay. And in particular, we've established that the length of a random Gaussian variable is extremely well behaved. Random Gaussian vector is extremely well behaved. Okay, and I'm claiming that's really all we need to know to understand our original application, which is that we're preserving the length of all these vectors as well as the distance between them. In fact, let's focus just on, we really only need to focus on is this first criteria. Okay. Why, maybe I should ask for fun, why does the first one roughly imply the second one? Generalizing the first one. In other words, the first one tells you that for a fixed set of n or polynomial n vectors, yeah, okay, you'll be able to preserve the length of all of them. So why does that give you the distance between them? Yeah. Yeah, so all the differences, right? So x minus y is one vector, and all the differences, that's n squared vectors, and you're going to preserve all n squared of these pairwise differences as well. So really all we need to worry about is preserving the one distance at a time and then taking a union bound over a bunch of stuff. Okay. All right, so, okay, so now, all right, so that brings us maybe to a slightly more focused lemma. Okay. So this one is really just focusing on one vector. Okay. So again, A is our matrix where everything's a Gaussian. All right, so you have k rows. Okay, and each of these rows uh, is a Gaussian vector. Okay, and we're saying that if I plug in an x, then this is going to be very well concentrated. All right. So maybe as a baby step, we can ask ourselves, what is the expected length of AX? The 1 over square root k is just going to shrink it down. It's not a big deal. So A is full of Gaussian random variables with mean 0 and variance 1. And x is some given fixed vector. Okay. So how should we break down the expected length of AX? Where can we start? X squared. You guys have already done this once. Better hurry. Yeah, okay. So let's write out the sum of squares of the coordinates first. Okay. All right, good. So now let's just analyze one of these coordinates. Okay. So what is, for some particular coordinate, right? AX I squared. So this is taking the ith row. So let's say that I call this row maybe lowercase a sub I, the ith row of the vector. Okay. So that I can also write this as the sum of AI xi all squared. Okay, so because that's how matrices work. Okay. Sorry, aij. Okay. Aij, that's how matrices work, right? Okay. All right, so we're working within row I, and I'm summing through all the columns j times the coordinate xj, right, squared. Okay. I'm claiming this is something nice and clean. In fact, what about just one of these coordinate pairs first? So let's take even one more step. What is this? Just one of these, yeah. That's fine. So, okay, what's one of these? What's an aij times xj? So xj is given, right? So that's some number. What is aij? It's a Gaussian, 0, 1. So what's xj times a Gaussian, 0, 1? Ah, it's a Gaussian. It's a Gaussian with mean 0 and variance xj squared. Oh, okay. Every one of these things is a Gaussian. Now, good news, right? Okay. Now let's not worry about the squaring. What about the sum of these over one row? Ah, it's a Gaussian. What's the mean? 0. What's the variance? Summation of xi squared. And the fancy way to write that, right, is the Euclidean length squared. Okay, so one of these rows are giving you a Gaussian random variable. The variance is encoding the length. That means, like, for example, if you did enough experiments and just did it over and over again and you measured the empirical variance, it's going to reflect the length of x. Okay? Right? So there's all these coincidences coming into play. So now what is this? Yeah, because that's the variance. Okay. All right, let's keep going back up. One more row. So now what is that? Kx squared. Okay. So that's why we're shrinking by k up top. Okay. All right, good. So what have we learned then? We've learned that each of these rows is outputting a Gaussian with mean 0, variance x squared. Okay. All right. Good, 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 good. All right. So okay. All right. So okay. So a fancy way to write that is that ax, which is a k-dimensional vector, okay, is, in our notation, every coordinate is a Gaussian with mean 0, variance x squared. All right. And what we're really asking is, what are the odds that the length is close to the expectation within a 1 plus or minus epsilon? Right? We're interested in the length of ax. Okay. How do I analyze that? Yeah. Okay. We have this kind of turn-off looking bound. We know that the length of a high-dimensional Gaussian vector is extremely well concentrated. Okay. So, okay. So for example, the probability that is greater than its expectation, which we now know is this, times 1 plus epsilon. Sorry for putting it at the end. Okay. We know that this is at most e to the negative epsilon squared k or so over 8 or some number. Okay. And likewise for 1 minus epsilon being smaller than 1 minus epsilon. Okay. But, modulo some facts, it's kind of, I could have, for example, just stated as mathematical fact that the high dimensional Gaussian is extremely well concentrated, the length is, right? If you knew that, then in fact, there's nothing too complicated going on here, right? AX, that seemed complicated, but actually it's just every row is another Gaussian, and then you get a Gaussian vector. And then, of course, Gaussian vectors are well concentrated if you studied that stuff for a living, right? Which people do, of course. But if you had assumed that was a fact and you were comfortable with these facts, then actually coming up with this very nice algorithm might not have been so crazy. Okay. So in fact, the guys who pointed this out, like Lindenstrauss is a famous mathematician, and when these guys get older, they have books about like their best 20 papers collected in a book or something. And of course, this paper about random projections is by far the most cited thing ever because everyone uses this thing. It doesn't make it a book. It's not interesting enough for his greatest hits. Okay. All right. So that's the basic idea, is that these random projections really are just taking advantage of the fact that high dimensional Gaussian vectors have extremely well concentrated lengths. Okay. All right. Any questions? Oh, after that, we choose k to be like log n over epsilon squared, and then you get the 1 over poly n, and you can take a union bound over all n vectors. Okay. Any questions about what happened? Everything happened very quickly at the end, so. All right, so in limited time, let me point out, we won't prove all the properties. I'll ask you to, however, read the notes a little bit. It's mostly calculations, but I want to maybe point out just a few of the highlights of the mathematical aspects. So, okay, so first of all, there is a better or more specific, not better, but more specific definition than nicest variable ever. So when we talk about continuous random variables, we talk about density functions. So this is sort of like saying what is the probability that x is equal to some particular value x. Okay, this is a little bit ambiguous, okay? But so it's kind of like saying, oh, what's the probability of being equal to this particular value x? And you can see that it's going down as it goes away from the average, and also as the variance gets smaller, which is what you expect. So variance is smaller, so the odds of going away from the average should get smaller and stuff like that. Okay. Now it's not exactly the probability that x is equal to x because the odds of it being any single point is 0. So the way you use a density function is you really say, okay, what are the odds that uh, x is, say, between a and b for given a and b, okay? And by definition of density function, that you're going to take the integral of this crazy function f of x between a and b. Okay, so for continuous random variables, we don't really say what are the odds of being exactly this. We only say what are the odds of being in this geometric space, right? Which makes sense. So the odds of being any particular point is 0. So that makes no sense, right? But yeah. Okay. So this might seem like a crazy thing. If you have taken, I don't know, undergrad analysis or something, you have probably done exercises like this. It turns out that actually these calculations work really, really nicely. So for example, you need the density to integrate to 1, right? Because the odds of being anywhere should all add up to 1. That is indeed the case. I won't do the calculations. They're in the notes. But also, if you integrate x f of x, that's asking what's the expected value of x. You'll get mu, and if you ask for the variation, you will get sigma squared. Okay, so things pop out nicely. There's some cute change of variables. That's sometimes why it's used as an exercise in some math homeworks. Okay. Oh, this is where I stopped preparing. All right. So, but I do want to point out something that's very important. Okay. So if we look at x being distributed from n Gaussian vectors, okay? And before we had said, okay, so for a normal Gaussian, f of x is going to be something like 1 over, square root 2 pi times e to the negative x over x squared over 2. So this is when I'm looking at mean 0, variance 1. Hopefully I got that right, okay? So if you're looking at n dimensions, could have been k, but I guess we're going with n here. So then I'm kind of asking, okay, I give n numbers, and what are the odds of the first coordinate being the first number, the odds of the second coordinate being the second number, and stuff like that. That's how we interpret a density function. Okay, so this will just raise this to the, well, no, it'll be a little bit different. So for the n-dimensional case, you'll get f of x is equal to, so this will be raised to the nth power, because there's one for each coordinate, okay? And then, well, okay, so initially you're going to get the product from 1 to n of e to the negative xi squared over 2. So this is just coming from taking the individual coordinates density functions and multiplying them all together, which is the case because they're independent. Okay. But what's nice, the same thing we always do is we can put the product inside the sum and stuff like that. Okay. So get the same leading term, but you get this negative sum, I is equal to 1 to n of xi squared over 2. Okay. Or to put it in a fancier way, you get the same thing here, e to the negative length of x over 2. Okay, so this was just a calculation, right? This is just multiplying the density functions of the individual coordinates together, nothing special. But this is really cool because it only depends on the length of x. Like you can swap coordinates, it doesn't change. Okay, but you can also rotate the space, right? So in general, good things should be rotationally invariant, right? Because somehow choosing your axes is somewhat arbitrary, right? You know, if I'm going to 3 dimensions, it can really be any three, and we'll always know what we're talking about. It'll be consistent. And that's what you get here. So if you rotated your space, rotations don't change the length of any vector. Okay. And so if you had rotated the space so that the individual coordinates change because you changed your axis system, but the overall length stays the same, you're just changing your perspective. And you will indeed get the same probability. I mean, the technical calculations will work out. Okay. So this is really important. The fact that a high dimensional, for multiple dimensions, the density function is just a function of the length, and it's rotationally invariant. Okay, and this actually is really all you need. Okay, so this actually explains why Gaussians add up nicely. The key lemma is what we just did, and then you'll see in the notes that the part where two Gaussians make a Gaussian is a simple application of this fact. Okay, and what else is there to say in the last minute? Not too much after that. So the rotational invariance, and I'll let you guys follow up in the notes, quickly leads to the fact that Gaussians add up to Gaussians. Okay, so that's extremely important. Uh, you're only like 5 minutes of reading away, so just do that. And then the last lemma that got that weird 1 over square root 1 minus 2t thing, is there anything to say about it? It looks like I just did the calculus very carefully, so just check that out too, and it'll be fine. A lot of calculus works out very nicely for Gaussian random variables because all these things cancel each other out. Okay, we're done. Thank you.